Hello, everybody. Good day and welcome to our second global R&D meeting, the second public one, I should say. First of all, thanks to everybody for all the positive feedback we've gotten from the last public global R&D meeting. But this was very rewarding and keeps being very rewarding and motivates us to keep working hard on improving the internet computer and producing all the results that we gonna present to you in these public global R&D meetings. Now, as last week or last time, we have again a very packed agenda with exciting updates and demos. So you will get an update on threshold, ECDSA, and Bitcoin integration. You'll see a demo on how you can turn a dApp into a decentralized dApp and using an SNS. Max will present then how to test your canisters with like SNS canisters such as Ledger and the Internet Identity. Then Lomesh will have some exciting updates about a new incubation program that will be launching. And then Adam will start the second round of demos presenting a very cool compilation optimization that makes things an order of magnitude faster in many situations. Then Claudio has some news on Motoko that I'm looking forward to. And last, but certainly not least, we have a demo from the community by Carbon Crowd. And I guess I'll leave it up as a guess challenge for you guys so that you can try to figure out throughout the whole meeting here what these guys are probably gonna talk about. Now we will start by presenting some metrics about the internet computer. And actually these make me very proud because they show how much the internet computer has grown and how mature it already is, despite being like a toddler with 16 months old only. So Ivanan, please tell us more.
Thanks, Jan. So my name is Ivanan. I'm a research manager here at DFINITY. Let's start by looking at the internet computer's burn rate first. As you probably know, canisters burn cycles for the resources they consume, including CPU, memory, bandwidth, etc. And the chart here depicts the monthly total number of cycles burned, summed up over all canisters deployed on the internet computer. Right when we started, there was a metric accounting bug, which didn't allocate and reimburse unused cycles for messages from other subnets correctly. Therefore, we only list the numbers for the last 13 months. It's really cool to see that the usage of the internet computer has been growing continuously. And if we even just look at this year, it has been more than tripling since the beginning of the year. Next slide, please. The second chart I want to present shows how many mainnet problems we've been dealing with. And as you can imagine, we've put a lot of effort into observability, adding logs, metrics, and alerts to know if something is wrong. And in case of such a situation, we first classify the incident depending on its impact on internet computer users. As an example, for a severe incident, we could take the outage of some boundary nodes, whereas a problem with the dashboard would be mostly considered major, and the connectivity problem affecting only some of the nodes would be minor. After the classification, we add information to our dashboard and gather experts to identify the root cause, fix it, test it, roll it out, and publish a post-mortem report for severe incidents. Not unexpectedly, right after launch, we uncovered and fixed a lot of issues. But over time, we managed to increase robustness, not just of the software, but also for our processes. As a consequence, the number of incidents has been decreasing steadily, even though we've been experiencing growing load, as we've just seen in the chart above. And please remember, despite all these issues, it's great that the NNS was never down and the ledger was always processing transactions. This is a great team achievement and I'm very proud of it. In summary, I agree with Jan, we are on a good trajectory. Both usage and robustness have been increasing a lot since launch. So let's keep making the internet computer even better. That's all from my side.
Thank you, Ivanan. And because as Diego mentions in the chat here, I also have to admit this chart really represents the quality of sleep I've had in the last couple of months. So, right, you see how much more happier I am today than maybe a year and some ago. Right, because since the last time, there's a lot of stuff that we have been working on that we have finished. Unfortunately, time is too short today to show you all of that, so we had to make a selection of what we would demonstrate today. But nevertheless, Samuel will give us a high-level update on the progress in the different areas and where we stand on our roadmap. Please, Samuel.
Thank you. Hey, my name is Sam. I'm VP of Engineering at DFINITY. And last month, we announced that we will change our road mapping format. We discontinued milestones and instead presented this stack rank list of features that we work on. We mark features that address community requests and communicate which percentage of our R&D team works in which area. We are confident that this new approach provides more transparency as to what the foundation works on and when the community can expect what. Since that last update, we made good progress, as Jan just mentioned, in many areas, even though this was August, a holiday month. You can find the new roadmap on internetcomputer.org. You see a screenshot here on the slide, and a shout out to the content team for the very nice design work. Please note that this roadmap is and will always be work in progress. So priorities change, things get added or removed, etc. And so since this last presentation, we also engaged with the community on various sub-roadmap discussions. For example, the SDK team was talking to the community about developer experience themes. And in parallel, our R&D teams have been preparing bottom-up what they consider important features and tasks to work on next. So with all of this, we continuously update and extend the roadmap accordingly. And I would now like to highlight our main achievements and upcoming releases. Let's go to the next slide, please. This is pretty much the same slide as shown last month, but there is a few updates on due dates, and we added two icons, one illustrating beta releases and the ship icon showing when we shipped something. Next slide, please. Let's start with the core protocol. Here we saw last month's demo on threshold ECDSA signatures and the BTC integration. Meanwhile, these APIs are released in beta version, and Manu will give you much more detail about this, that you can actually start building on it in a little moment. We also demoed HTTP out calls. Here we expect the release in about 2 weeks. Next slide, please. Next is boundary or boundary nodes. We made extensions to the internet identity to now support custom domains. We are still working on a mainstream solution for custom domains, but even today, developers can use solutions such as IC-Front to serve their dApp from a custom domain while reusing the same existing II identities. A few days ago, the team managed to switch all boundary nodes to the ICOS VMs. This is a key precondition to eventually hand over control to the NNS and fully decentralize boundary nodes. And talking about decentralization, we made also good progress on defining a target architecture to better decentralize boundary nodes altogether. We are preparing a write-up that explains all of this, and we plan to publish this in the next days and look forward to your feedback. Next slide, please. That is about system utilities and dApps. The Geeks team is continuously updating the NNS frontend app, and these updates include big changes, but also smaller ones. For example, one that I appreciate every day is the asynchronous handling of NNS voting, a really significant UI improvement in my life. We are happy that the community also recognizes these achievements and improvements, and we really value the feedback. Second topic in this area is the ICRC community supported token standard. We were working in a working group with many community representatives on this standard. We first had a first draft version, received some constructive feedback, then therefore took another loop, made additional improvements, and then the second draft version was overwhelmingly approved by the working group, and then also clearly adopted by the NNS. We are very happy about that and implement a ledger accordingly. Next slide, please, is about governance. Here, our main focus is the launch of the SNS. I'm looking forward to an extensive demo later on in this meeting. It's super motivating to see how all the building blocks are now coming together and build this system. One of these building blocks is the community fund. And the community fund enables Neuron holders to invest in the tokenization of dApps. The community had honestly mixed feelings about the community fund, but ultimately the NNS proposal was narrowly adopted and we started working on it. Next domain is developer experience. Here we saw last month the themes and the key features that the SDK team is working on. When discussing them in more detail with the community, we often received the request to also talk more about Motoko. And to do so, we plan, and you will see a more extensive presentation on Motoko, what we have achieved in the past months. We are still working out more detail as to what we tackle next, and stay tuned for more on that. Finally, last but not least, last slide, please. Oh, sorry, I missed one slide change. One more, please. The last part here is infrastructure and operations. The team just completed tests of the next generation replica node hardware. We focused on one vendor for now and plan to extend it to additional vendors in the days and weeks ahead. And we are going to publish the results and also this new hardware spec in the next days. And then finally, the team has made a major effort to switch our build system to Basel. This leads to build times that are up to 11 times faster compared to today. This is a huge improvement for software engineers building the IC code on a regular basis. I hope you share my excitement about all these great achievements. And with this, I hand back to you, Jan.
Thank you, Samuel. So last time we have seen a demo of Bitcoin integration or other Bitcoin testnet integration. And I'm sure many of you have the same question on their minds as me, namely, when can we finally get the code Bitcoin? Manu, tell me.
Hey everybody, I'm Manu. So I'll give a quick update on the Threshold ECDSA and Bitcoin integration progress. First, I'll briefly cover the what, why, and the how, and then I'll share a little bit more about where we stand today. We're building two main features. The first is this ECDSA, which allows each canister to have access to their own public key of a digital signature scheme that's called ECDSA. And so the canister can now programmatically request messages to be signed under that public key. And we want this because this allows many things, but among other things, it allows a canister to hold crypto assets natively on their own blockchain. So a canister can now hold Bitcoin or Ethereum because these blockchains use ECDSA signatures to authorize transactions. But it's actually much more broad than that. So it's not only many cryptocurrencies that use this. Also, just in general, ECDSA signatures are very widely used. And so having the ability to sign messages and having their own public key allows a canister, for example, to authenticate to the outside world, to many existing systems, or maybe even sign certificates. I think there's a lot of opportunities there. And how do we do this? Well, we do this building on threshold cryptography. We don't want this secret to just be on one machine somewhere that would not be secure. So we use threshold cryptography, meaning that all the replicas of the subnet each have a part of the secret key. And if a canister requests a message to be signed, then some multi-party cryptographic protocol takes place such that the replicas collaborate to make such a signatures. That's ECDSA. we're also building this Bitcoin integration, which allows canisters to read the state of the Bitcoin blockchain. We want this because with that access to read the Bitcoin blockchain in combination with the ECDSA functionality, you can now write smart contracts on the internet computer that control Bitcoin. So you can have your own address derived from your public key, and now you can also read the UTXOs that you have and see whether you received Bitcoins or not, and you can now send them around. And so this allows you to write Bitcoin smart contracts on the internet computer, and it brings in the Bitcoin liquidity into the IC ecosystem, which looks like a good thing. How do we do that? In a similar way, we want to rely on the replicas of a subnet. So the replicas of the subnet reach out to the Bitcoin network and obtain the latest blocks, and they reach agreement on it. And now the state of the Bitcoin blockchain is stored in the subnet state. And so what's important is that we don't want to rely on like some external set of parties or some external bridge, which would require new trust assumptions. We want that the subnet itself, the replicas that you already trust, do this work. Next slide, please. So as Jan already mentioned, people are very excited to have this. So where do we stand? So we have the beta release is live now. So today on the internet computer, you can use these features, but they're experimental, meaning that there is an ECDSA key that you can use, but it's a temporary testing key, so you shouldn't attach any value to it yet. But it works, and you can actually use it. And similarly, you can read the state of Bitcoin, but it's limited to read Bitcoin testnet state. So this is available. We've published documentation, and we're in the process of publishing more videos explaining how to use this. And yeah, everybody can build on this right now, and we've already seen very exciting prototypes being built. And in the meantime, we're working on making sure everything is rock solid. So this is, of course, quite security sensitive, so we want to make sure we get this right. So we're working on more code audits and security reviews to make sure it's all rock solid. We're working on the performance such that we can run this on a larger subnet, making it more secure. And last but not least, we're working on this CKBTC, which is like wrapped Bitcoin, but the wrapping is done by a canister instead of by some maybe central party. And so we expect that this is on the roadmap marked for 2022. We expect that we maybe need 2 more months or so for this. And in the meantime, you can build against the beta release. And then once the GA release is ready, you can switch your dApps to target those APIs, and then you're in business from day one. Yeah, that's it from my side. Back to you, Jan.
Thank you, Mani. Looking forward to all those canisters that deal Bitcoin in one way or the other. So let's turn our attention to demos. Next up, we have Adam and David, who will show you how you can take your dApp and have the internet computer to issue tokens for it, raise funds for you, and decentralize your dApps with a push of a button, or rather proposal to the NNS. And I really do hope many of you becoming successful entrepreneurs with what we have for you. So please, Adam, show us how this works.
So actually, I'm Pete, so not Adam, and I'm a product manager here at DFINITY. And before we dive in with Daniel and David and run through a demo of the SNS, I just wanted to say a few words and set some context. Now, I know many of you have been waiting a long time to see the SNS, so I'll try to do this quickly. And please be patient for 1 minute longer whilst I summarize this for some of the newer members of the community. So first of all, what is the SNS, and more importantly, what does it mean to you? So for developers, the SNS is a solution for easily creating DAOs and transferring their projects to becoming owned and operated by a DAO. For users and IC community members, the SNS offers a trusted path to participate and become members of those DAO communities. But why, you ask, would we need this? Why would anyone do this? Why do this on the IC? And why should anyone use the SNS to do this? So at a high level, we see these 3 reasons. So first of all, more generally, DAOs principally originated to solve the problem of who controls and updates mutable smart contracts. The solution being to decentralize and hand control and trust to the community of users of those contracts or dApps. And the tokenization of governance also brings users and developers together onto the same team, which engage the community and aligns growth incentives. So DAO creation is really an important plank of any blockchain which supports smart contracts. So secondly, and specifically to the IC, DAOs on the IC bring real meaning to the word autonomous in DAO. Because dApps can be 100% on-chain, DAOs can truly control all of the code of the dApp. Thirdly, the SNS specifically provides a path for projects that wish to create DAOs via an already decentralized DAO, i.e. the NNS. The NNS plays a key part in ensuring trust in both the DAO creation process and the ongoing operation of those DAOs. So bringing this back down to earth a little, what does the SNS actually practically look like? So you can think of the SNS as a toolkit comprised of kind of three parts. The canister code that provides governance and ledger features. This is open source and free for anyone to use. A dedicated subnet, which ensures that SNSs using that subnet, DAOs can trust that the code running there is always on verified versions. And then finally, a launch pad, which makes it easy for users to participate in the creation of DAOs themselves. I've probably taken too much time at this point. The demo is quite involved. So I'm going to hand over to David and Daniel now to show you how this works in more detail.
Thanks, Peter. Can I share my screen, please? I believe that's working now. All right. Hey everyone, my name is Daniel. I'm an engineer on the NNS team, and I have my colleague with me, David Del Busco, who's representing the Geeks team. Today, we're going to be showing the latest changes to the SNS and the NNS dApp to support that. So we have quite a bit to get into, so I'm going to dive right in. A lot of you may have seen this diagram before in some of our previous demos. It showed the discrete steps that a dApp developer and an end user will take when interacting with the lifecycle of an SNS. Before I go into and describe each of these steps, I just want to quickly go over the different components of this diagram. At the top, you can see a picture with me in it. I will be representing the dApp developer within this diagram. All the steps that I show are something that the dApp developer will go through when trying to create an SNS. Below, you can see that same picture with David, who will be representing the end user. He'll be describing all of the UI changes and what a NNS voter and SNS cell participant will experience. Within this gray box, we have 4 different tracks. The top of the track represents the already deployed dApp to the IC. It'll show the entire lifecycle of the dApp throughout the process, most importantly, who controls it. Below that is the NNS subnet track. This includes all of the canisters deployed to the NNS subnet and all the interactions involved with deploying the SNS. Below that, and later on in the timeline, you'll see the track for a single SNS that's deployed to the SNS subnet. Note, this is just showing a single SNS as there's a one-to-one relationship between a dApp project and an SNS. And finally, this is the UI track that'll just show the different interactions at the different stages of the SNS lifecycle. So let's actually go and look at some of these discrete steps in a little bit more detail. And of course, I'll be cycling back through these slides later on when we're actually executing these commands. So first up, this box is going to show that we have a dApp already deployed to the internet computer. At this point, the dApp should be solely controlled by a developer. There should be no other person who can update that mutable smart contract. If a user was to navigate to the UI, they can now click on a launch pad. At this point in the demo, we won't have anything in there, but when this feature is launched, any user of the NNS can go in and look for proposals to vote on for sales and also to be able to contribute and participate in sales. So this is the first really big step that's going to happen. As Pete mentioned, the SNS is for transferring controllership and decentralizing control of a dApp. We do this through a DAO that was based off of many of the lessons learned in the NNS. And in this step, the developer will initialize the SNS by a call to the SNS WASM canister. The SNS WASM canister is what provides those secure NNS-approved WASMs for the SNS, and will actually take the configuration that a developer needs and spawn a SNS on that protected subnet. With this SNS created, there won't be anything really it controls, and it's up to the user to actually surrender control of the deployed DApp to the SNS. Once that control is surrendered, they can start the automatic process of decentralization. That's accomplished by an NNS proposal that, as soon as it's kicked off, is completely out of hands of the developer and is executed on the protocol layer. This proposal is like any other NNS proposal where neuron holders can go vote to either adopt or reject. And if adopted, the process continues in the decentralization. That process is known as a decentralization sale, where anybody can go and log into the NNS DApp and be able to participate in the sale given their accounts. Once the parameters of the sale have been met, the sale will automatically end and the results are committed. Once the results are committed, these SNS neurons are then distributed to the participants, which we can see in the UI. You can go and view. Finally, as Pete mentioned before, the superpower of the IC is mutable smart contracts. So one of the most important things that we want to demo here is that after the decentralization sale, the constant evolution of a DApp is still possible through this decentralized governance, very similar to how we do it in the NNS. So now let's get on to the demo. To quickly demonstrate this stage, what we have for our demo is just a very simple smiley DApp developed by our very own product manager, Pete. Thank you, Pete. It's a very simple DApp that has two canisters, one front-end assets canister that queries a back-end canister. When we actually demo the upgrades of our DApp, that's what we'll be changing. We'll be updating the back-end canister with a new color. So now that we've shown that, I'm going to skip over showing the launchpad before we have anything populated into it, and actually just go into the stage of deploying an SNS. So a developer has a project and they have a DApp and they want to customize this SNS so that they can have the parameters that make sense for their project. So what does that look like? Well, the SNS team vends a command line tool called this SNS CLI. And that provides a YAML file where you can specify all of this configuration. There's lots of fun stuff like what your token name is, what your token symbol is, and other things like a logo and an SNS governance name. Most importantly, for this demo, we want to specify sale parameters. These are very important to get correct because as soon as the SNS is deployed, these sale parameters are immutable until after full decentralization is reached. You can specify things like the max targeted ICP we want users to contribute, at which point the sale will automatically complete, and also some basic things like what the minimum ICP we want for the sale to even succeed. Also, we can configure how many participants we want, so you can target your decentralization factor, and how much each of those participants can contribute, both a minimum and maximum amount. Now, don't worry, if any of these steps fail during the decentralization process, we also have mechanisms that will return the DApp to the original DApp developer, so no data and no projects are lost during this process. Most importantly, and one of the most interesting things you can configure here is how initial neurons are distributed at Genesis. So this can be given to developers who want to be entrepreneurs and find a way to fund as well as reward themselves. But as the SNS toolkit that Pete was mentioning before, we do have quite a bit of validation and verification that full decentralization is reached before an SNS is even deployed. If somebody tries to attempt to write something that's a rug pull, our tooling will make sure that that's not possible. So I've just gone over that configuration file that's very specific for my Smiley DApp project. I'm going to actually go and initialize my SNS. This is very simple. Again, I'm using the SNS CLI tool, and I'm just pointing to this configuration file. I've created an example demo where the participation sale is very simple. We're just looking for two participants to both contribute one token each. And once that's reached, we'll actually be able to automatically complete the sale, and you'll see the full decentralization process. So what's happening now is I've issued a request to the SNS WASM canister, and that has just taken the most secure WASMs that are at the tip of our development and deployed them to the SNS subnet. You can see that it's just given me information such as the subnet ID and the canisters that were deployed. And now I need to do that part I was talking about earlier, where I hand over the controllership of my DApp to the SNS. What this looks like is just some very simple DFX commands that I'm printing out to my console. You can see that I use add controller and remove controller to remove my developer principal ID and my wallet, and adding the SNS root canister. Once this is complete, I can notify the root canister that there's a new DApp under its control, and will actually have accomplished surrendering of the DApp to the SNS. So this will just take 1 second more. I believe it's going to print out the happy sign, and it looks good. We can now see that my Smiley DApp has been transferred over. So now that's the first part of going through the full decentralization. This is the last step that a developer will take before it's completely out of their hands and done at the protocol layer. And that's when we submit an NNS proposal for voting. So this is very simple. I just have a very simple script that'll send this out. It looks like it's made the proposal. And now let's actually show some of the changes in the NNS DApp. I'm going to hand over speaking to my colleague, David, who will walk us through that as the end user.
Sure, thanks, Daniel. So as you have heard along the demonstration, we have called something new, which is the Launchpad. So if you open the menu, that's going to be the one new screen dedicated to the SNS project in NNSD app. In that screen, you will find the ongoing sale, like all the SNS projects that are on ongoing sales, and you will also find all the proposals that are related to start new SNS sales. It's worth to note that these proposals will also be listed in the, I would say, normal voting tab, but it's convenient to have all the SNS information at the same place. So to go on with the demo, I would say we can open that particular proposal. And here it's a standard NNS proposal. So at the end of the day, there is nothing new in the display. It's like the topic, the title, the payload, and so on and so on. And you can find all the information regarding that sale. So I would say, let's accept it to go on maybe, because yeah, we want to see that in action. So while it's voting optimistically, it should be accepted, I guess, executed, even better. So if we go back to the Launchpad and refresh it, assuming that I'm an investor and I know that when the proposal is going to be finished, I come back to the Launchpad, then I should find the project that are currently on sale. So of course, here we're just going to have one, but ultimately I should find more. And once it's loaded, because the Launchpad is exploring all these projects that are currently on sale. Yeah, almost there. You see here, we don't have the proposal anymore, of course, because it has been executed. And now we have that project, which takes the parameter we have seen before in the YAML file. So we have the logo, we have the name, and we're going to find all this information like the minimal commitment, maximal commitment, the duration, and so on and so on. Exactly. And yeah, so it's open to participation. So I'm a small investor. I want to participate. Oh, actually, I'm a good investor. So I'm going to invest a bit of ICP until the max I can commit. Then I can have review what I want to do, and I can execute my participation. It's worth to note that if I don't commit to the maximal allowed per user, I can come back later and increase my participation if I want until the max. So while it's committing, then Daniel gonna do that also for the second user, because I think we have set 2 users, right? Yeah.
That's correct, David.
Excellent. So yeah, I think if we refresh now.
Yes, I'm refreshing as the other participants' transaction just went through.
All right, super. I like there is a bit of waiting.
Ooh, drum roll, please.
Yeah, exactly. So, mhm.
In the meantime, as this is refreshing, we know that the sale is completed. So we've just queried for the sweep results. We can see that 2 neurons were distributed to these sale participants.
Yeah, exactly. Completed. All good. So when it comes to that launchpad and the sale itself, it has been completed. So maybe we can show the next things that gonna be a bit new and proposed in NSD app. So as I received neurons, yeah, I should be able to find these neurons. So what you're gonna find newly on that particular page, and ultimately also probably on the accounts and the voting tabs, is that new drop-down that lists all the projects that have been successful. So in that case, I can select the Smiley Day app, and here I find the neuron that I received. So we have said that I have just 1 neuron, that's why there is just 1 listed. And if I open it, I can find the details. And at the moment, there is a single action that can be performed. It's adding a hotkey that can be useful, for example, if like the app developer implements some SNS functionality for the governance in this app. Yeah, so.
Great, thanks, David.
You're welcome.
Yeah, so we just saw what the end user's perspective is on how to participate in the decentralization sale. I know that was a lot of button clicking, but I do want to reiterate a couple points that are exemplified within this diagram. 1, the sale opening and closing, as we can see, was completely autonomous and executed by the NNS, which is a decentralized DAO. Because of this, once the NNS proposal is adopted, it can then set the open and close sale window, which is all done at the protocol layer. There is nothing past submitting the NNS proposal that the developer has any control over. And once the decentralization sale is complete, the governance canister, which controls all of the actions that a decentralized government can do, is unlocked and operations continue as normal. So the final thing I want to show, I know we're running out of time, so I'm going to quickly go through this, is the actual upgrading of the DApp through this decentralized governance. I've shown this a couple times, but this Smiley DApp, we have the backend hard-coded color. So I'm just going to change it to something very simple and rebuild the canisters for deployment. So I, as the developer, am no longer the controller. I have to use SNS governance to go and evolve this DApp. The way I do that is I use one of my neurons, and I'm going to submit a proposal to that SNS to upgrade the DApp. We use SNS Quill, and via SNS Quill, we're just going to use that WASM and submit it. And I'm going to use one of the newly created neurons to go vote on that. This should give us a majority on the voting power. So the proposal should be automatically executed. And if we go over to the Smiley DApp, we should see it change color. This is done via an upgrade process. So of course, the SNS governance canister is calling to the DApp to shut down, to upgrade to this version, and then to restart. Hopefully this won't take too long, but as you see, we've had some network connectivity problems. So I'm hoping this goes fast. Let's see, maybe I can inspect the console. We can see how it's doing. Great, so we've already lost connection, so that means it should refresh very soon. Let's see. Maybe I'll refresh it to give it a fresh start. So we should see it turn green. Pending. Ah, there we go. Sorry for that delay, folks. Well, that's pretty much it for me. I just want to quickly go in summary of everything that we saw in this demo. From both the developer and the end user perspective, we saw how to deploy an SNS, hand over control, begin and complete the decentralization sale, and then manage, adapt through an already decentralized DAO. I want to give a huge shout out to all the teams who have been working on the SNS initiative and to the patient community who I hope will enjoy this. Also, very special thanks to my reoccurring demo mate, David Del Busco, who's been trimping through this with me, lots of SNS demos. That's all for me, folks. Feel free to ask any questions in the chat and I'll try and answer.
Thanks, everybody. Thanks, Daniel, David, and surprise guest Pete. It's such a pleasure to see this all coming together, and I can't wait to participate in decentralized sales for Smiley dApps and many other dApps in the coming months. So as a pain point of many developers today is like testing and debugging canisters that interact with NNS canisters such as the ledger or internet identity. And in our second demo today, Max will show us how much easier life has become. And indeed, I mean, will also be the way how people can test drive an SNS and all of that we've just seen. Please, Max.
Sure, yes. Hello, I'm Max. I'm from the Geeks team. And so I'm the team that makes the NNS dApp, amongst others. And I would like to talk to you today about testing, as Jan mentioned. So the NNS dApp protects well over $1 billion worth of ICP. So we take testing very, very seriously. But we found that creating a test environment with NNS canisters is quite hard. We did it, we managed, but it was hundreds, thousands even lines of shell script. We had to deploy patched canisters, and even some members of our own team with M1 Max struggled to compile all the parts they needed. So basically, we could test reasonably thoroughly, but the setup was very complicated. But as soon as we had it working, other people approached us saying, hey, we need to test against the NNS. We too need something similar to what you have, either for locally playing around with DNS without spending real ICP, or because we need something in CI. We also realized that the demand for this was going to increase as more and more members hand over control of their dApps to the community via something like SNS. So what we've done is that we have tried hard to make it as easy as possible for everyone, so every single developer, not just us, to install the NNS locally, interact with it, test with it, and use it in their projects. So what does this look like? May I share my screen, please? Okay, so we start off as a local developer. You start your local DFX server with start clean, basically just as always. And once the local server has started, there's a new command that you can use, or that you will be able to use as soon as it's been released, which is DFX NS install. And what that does is that it installs all the NS canisters on your computer locally. It's not anywhere else. And it configures them just enough to be useful. So uses that we imagine are, well, we start with
Max, do you want to share your screen?
We cannot see anything.
Can you not see anything? Oh dear.
Oh, well, we see your face, but that's it.
Oh dear. Can you, oh dear. Can you see my screen now?
Yes.
Okay. Well, I apologize for that. So what I did up here was that I did DFX start clean. So basically starting a local DFX server, and then I ran this shiny new command, which is DFX NS install. And what that does is to install all the NS canisters and configure them. So in particular, it installs all the normal NS canisters that you see in production, but locally on your machine. So the registry, governance, ledger, and so on. So if you are doing financial integration and you want to test without real ICP, you can use your local ledger. If you want to play around with governance, then you again have a local canister. And we thought that maybe it's sort of a bit user unfriendly to just have invisible canisters. So we also packaged the NS dApp. So the NS dApp is sort of basically exactly the same as the production one, and it gives you a bit of a view into what's happening on the NS. You will find that the locally deployed dApps are almost identical to production, but they've been tweaked slightly to make them easier to test with. So for example, if you look at the capture is always the letter A. So if you want to use this in your CI, your bot, your testing code can automatically fill in the capture. Of course, we don't want this in production, but locally, you have everything needed to make testing easy. Then if we get to the actual NNS app, you will again see that this contacts your local governance canisters, your local NNS canisters, and they're all real values, kind of real in your local context. So you have your usual main account. You have a special extra button here. So, or you cannot buy ICP in a normal way, but you can get yourself ICP in this way. And once you have ICP, you can also buy yourself neurons and vote locally. Actually, during setup, as part of making the NNS useful, a few proposals were already passed. And so if we look into everything that's been made, you will find, for example, that I've already set some authorized subnets so that you can create canisters and SNS. So one of the applications that we think are probably going to be most important. So we already have, okay, if your DApp uses internet identity for login, you have a local internet identity, which is great, probably a very common use case. Financial integration. But the last one, you've just seen a demo of how to perform an SNS. Taking your DApp that you've been working on for many, many long hours and handing it over to the community is quite a big event. You're sort of saying goodbye to your child. You're letting go control, and you get one chance to get it right. And we would hate for that to go badly wrong. So you can perform the demo that you've just seen locally on your own computer to practice, to experiment, to see what it would look like. Anyway, that's all from me. Thank you for your time.
Thank you, Max. Great work. Next up is Lomesh, who will tell us some more how we support developer teams. And yeah, Lomesh, please take it away.
Hey everyone, this is Lomesh. I'm the Vice President of Growth at the DFINITY Foundation. Can we move on to the next slide, please? Thank you. So as a foundation, we are always looking at opportunities on how do we better collaborate with the different community developers and ecosystem projects that are building. Together, like we've been kind of brainstorming on this a lot, and I think what better than us kind of meeting in a physical space and kind of collaborating together. So we came up with this, we're introducing ICP Lab, which is essentially a co-working incubation program, which will facilitate stronger collaboration between DFINITY team and our ecosystem projects. So this is essentially going to be a 1 to 3 week on-site program in Zurich, our DFINITY headquarters in Zurich, where we will essentially be sponsoring various teams that will be coming in, including the airfare and lodging. And each of these teams will essentially come to our headquarters where they'll have an opportunity to collaborate with different parts of DFINITY team, like most importantly, of course, the R&D team, where we'll be kind of working, sharing knowledge, exchanging opportunities. Teams will essentially have an opportunity to present their projects and have, let's say, different engineers from our team help out with various different aspects, including, okay, what should be the right architecture, how do you kind of scale this, and all sorts of such aspects. There will be also tailored workshops from our team, as well as like whiteboarding sessions with different parts of DFINITY, R&D, growth, legal, marketing, and so on. Next slide, please. So in terms of like initially how we envision like kind of starting this program, and we can expand the eligibility set, but for now, we will be focusing on teams that are currently building on IC already. So making sure that like these teams have already started taking a deeper dive. They have already received either a developer grant or some seed investment. So these are teams that are not super early, but they at least have some prototype and they have been kind of diving deeper, because then we can really be sure of that, okay, they have some real problems that they're trying to solve, and we will try to, our team will learn from their problem pain points, and then we'll simultaneously also be able to help. So the pilot begins with on September 12th. So we're inviting Infinity Swap team as a first pilot, try to kind of go through how the process works, like learn the different kinks. But I think very soon thereafter, we'll be also rolling out an open application and submittable, very similar to how we do our grants program, where the teams will be able to apply, and then there will be an evaluation and interview process. Once approved, then the team will work to align the visit schedule as well as the programming during the course of things. And then we'll look forward to meeting various teams in person in our Zurich headquarters. Thank you, everyone. That was about it.
Thanks, Lamesh. I'm looking forward to meet all these teams and in particular to learn about all the new exciting projects they are going to build on the Internet Computer. Talking about stuff running in the Internet Computer, let's go back to demo mode and about the next one you might have heard already on Twitter, because OpenChat tweeted about how happy they were that now upgrading all their canister became 10 times faster. I think it's something from 40 hours down to 4 hours. So Adam, please tell us about how that happened.
Hi, everyone. My name's Adam. I'm on the runtime team, the group that's responsible for actually running your canister code on the IC. I'm going to talk about this optimization we did. So what did we do? We basically sped up this compilation process that happens within the IC. Why? It just leads to faster executions in a lot of situations, like these installs for horizontally scaled apps, or cold queries when we need to spin up a new sandbox. I'll describe this more later. And how do we do that? We basically started caching this compilation step that occurs within the IC. So what do I mean by this compilation step within the IC? Well, when you as a developer write a canister, you're going to write it in Rust or Motoko or TypeScript or something. You're going to compile it to WebAssembly, and that WebAssembly is what gets installed on your canister. Now, when we actually want to execute your canister in the IC, WebAssembly is not directly executable on our machines. It's not machine code, right? So first we have to do some validation and instrumentation to make sure your WASM isn't doing anything it's not supposed to do, and the instrumentation allows us to check how many instructions you're running and figure out how many cycles to charge, things like that. And then once we have that validated WASM, then we use WASM time to compile it to actual machine code, which we can execute. So these last two steps, which I've circled in green, are what I'm referring to as compilation in the rest of this talk. I'm going to quickly say what the old state of the system was, then I'll say what the new state is with the optimization, and I'll give two examples about how it improves performance. Next slide, please. So we introduced sandboxing a while ago for security purposes. Basically, we don't want to run your canister code in the main replica process. We want to spin up separate processes for each canister. And when your canister gets installed, we'll spin up the sandbox, the main process, which has all the canister data. We'll send the WASM over to the sandbox, which then goes through this compilation process I just described to execute messages on your canister. So this happens anytime you install or upgrade a canister. It's also possible that your sandbox process gets evicted. We can't keep them all around forever. We have to clean them up sometimes. So if your canister hasn't been active, the sandbox may be evicted, in which case we lose all of this compiled machine code. And then when you want to execute a new query, we have to go through the whole process again of spinning up the canister, passing over the WASM, and doing the compilation. So both these processes can be rather slow. Next slide, please. So now we have introduced an optimization where within the replica process, we store a hash map from WASM source code to a serialized version of the machine code. And what this means is that as long as that WASM source has been compiled at some point in the past, then whether you're doing an install or you're respawning a sandbox process, we can just take the already compiled machine code and pass the serialized version over to the sandbox process, which can immediately do the execution without going through any of the compilation steps. So this is going to improve situations where you have horizontal scaling, that is, you've designed your app in such a way that you have many canisters with the same source code. For example, you've been doing some sharding where you have a bunch of canisters handling your data, and they each have different data, but they have the same code. Or for example, if a bunch of people are using the ACID canister on the same subnet, all those ACID canisters will have the same code, just have different data. And so then anytime one of those canisters gets installed, we don't actually have to do any compilation. And again, even if no other canister is using your code, if your sandbox gets evicted and then we have to respawn it, we've compiled your code from that canister on a previous run and we don't need to recompile it. Next slide. So this is just an example of the benefits, which we see from OpenChat, just because it's an example of an application that uses this horizontal scaling architecture. They have one canister per user, which is about 30,000 at the moment. And their upgrades used to take forever, largely because each and every one of those canisters would have to get recompiled. And after doing this optimization, as Jan said, it went from about 40 hours to like 4.5 hours now, because they do the compilation once and then every other upgrade just has to do the pre and post upgrade hooks, but skips this compilation step. So if you design an app similar to this, where you have many, many canisters with the same source code, then you'll get this benefit too. Next slide, please. And so for example of these tail end query latencies, as I said, if a canister isn't active for like a minute or so, the sandbox may be evicted, which means that the next time a query comes in, we'll have to respawn the sandbox. And this is what I refer to as like a cold query in this example. And they can be a little bit slower than a normal query because we have to spawn that sandbox and set everything up. And before this optimization, this is an example of a specific benchmark I ran just on an example canister. This example canister takes 220 milliseconds to compile, which is a bit on the small side, but pretty typical for a lot of canisters we see on the IC. And in the example, I ran a very fast query, a query that takes less than 1 millisecond to do the actual code to execute it within the replica, which is a pretty fast query. So for this example canister, if you would run a query against the cold canister where the sandbox has been evicted, it would take something like 240 milliseconds, because we'd have to spin up the sandbox, do this compilation before we can run the query. And with the optimization, these cold queries take like 10-ish milliseconds. We still have to have some overhead, but that compilation step is skipped. And so they're just much, much faster. So this benefit should basically come to any canister that has non-trivial compilation time, and you're sometimes running fast queries against. The actual factor, the actual performance improvement will depend on how that compilation time compares to the query time, but I think this is pretty representative of a lot of situations. Next slide. This is just basically reiterating what I've said before, how we can skip the compile step, but I think I'll skip saying too much about this because we're a bit behind time. So that's it for me. I'm done.
Thank you, Adam. Great work. And I mean, this is just one example of the many optimizations that have been doing over the last year. Some of them are more visible, some of them are less visible. Yeah, thanks everybody for that. It has been a while since we've talked about the Motoko last in the R&D meetings. And so, yeah, please, Claudio, take it away with all things Motoko. Thank you.
Sure, thanks. So first of all, Adam, that's actually a great optimization for Motoko, because we let you horizontally scale identical code and you can take advantage of your optimizations. So what is Motoko? So just introduction, I'm Claudio from the languages team, and I'll just give you this update on what we've been doing on Motoko. But before that, I need to introduce what Motoko is, and Motoko is DFINITY's native programming language for the IC. So why a new language? We always get asked this. Well, we wanted a language that was tailored to the IC with dedicated syntax and typing rules. It was also compiled for the IC, so optimizing for things that the IC cares about, so cycles and code size. And we want a language that is safe by design with a sound type system, no silent overflows, and garbage collection, so users don't have to worry about manual memory management. But we also want a language that we could control so that we have the freedom to innovate, adding features that are specific for the IC. So how have we done this? Well, Motoko's been going for 4 years, but we've got a kind of growing diverse team of people with various interests, like in DX, runtime systems, type systems, compilation. We adopted a principle of modern design using modern programming language techniques. We tried to choose very natural abstractions for the low-level features that the platform provides. So although we expose all the features, they might look slightly different in the programming language. And we did this by choosing familiar syntax and concepts that hopefully people will be familiar with, so it's not a foreign language. And we chose a design that was really actor-based. So in Motoko, a canister is just an actor, and actors are a well-known concept from programming languages. They're kind of isolated event loops that communicate only by asynchronous message passing. So since 2021, we focused mostly on scaling to larger canisters, to achieving parity with the system API that's exposing all the low-level features that the IC provides in a nice way. We've also tried to add some high-level, some high-value language features that will benefit most of our users, and to improve our tooling in general. But the other thing we've improved is Motoko Playground, which is a very popular way for experimenting with Motoko and deploying to the real IC, and we've got a demo of that coming up. So regarding scalability, for upgrades at scale, we've implemented streaming stabilization of stable variables. Now, we used to need up to 2 gigabytes of headroom in order to do an upgrade for various reasons. But now with the streaming implementation, we just need 32K of overhead to allow our upgrade to succeed. And by doing this optimization, this actually enables us to use heap sizes of close to 4 gigabytes. The previous limit was actually 2 gigabytes, so half of memory wasn't available. Half of WASM memory wasn't available to Motoko programs. And now we should be able to scale better pending other features that are coming online soon. We've also added a new library for low-level access to 64-bit stable memory. And this library is backwards compatible with high-level stable variables in Motoko. So you can use a mixture of both and they won't interfere with each other. That way you can have your cake and eat it too. And we also added a query that users can use to monitor the storage size of stable variables. And that means programmers can, by being careful, improve the reliability of their programs. So these are all scalability features. Regarding, next slide, please. Regarding parity of the system API, there's a bunch of system features that we've now exposed in Motoko. So there's users can implement canister heartbeats using a system method. Users can flexibly inspect ingress messages to mitigate DOS attacks. Users can measure the instruction counts of code using the performance counter exposed by the IC. And users can issue dynamic calls to canisters, sending and receiving raw binary data, which is useful in kind of niche applications. Next slide, please. More general new language features we've added is we've implemented destructuring imports, which let you access individual library functions, avoiding the heavy dot notation. We've added a type level and an OR to let you concisely derive new types from old types without repeating yourself. We've added to-candid and from-candid operators to provide first-class in-language serialization. And that's useful in conjunction with both dynamic calls, where you need to serialize arguments and deserialize results, and also for use with stable memory, where you need to serialize to binary representations. We've also added object combination extension syntax that lets you construct new objects from old objects by concisely merging and overriding fields, all in a type-safe way. And actor classes have been improved to support additional features. So you can specify canister settings when you instantiate a new instance of an actor. And you can also upgrade existing actors, both of which were features that you couldn't do prior to recent releases. Next slide, please. So in terms of tooling, we've added an upgrade safety check to DFX. So this means that when you do an upgrade, DFX will check that it's compatible with the installed canister. It'll verify that interface changes won't break clients, and it'll verify that stable variable changes won't lose data. So it's a safety feature. Our VS Code extension has seen some more love. We've got better highlighting and navigation. We've got validation of JSON project files, or dfx.json files, and support for multi-canister projects. So in the past, you could only work on one Motoko actor at a time. We've also published a new WASM toolkit, IC WASM. That's kind of general purpose, but aimed at the IC. And we've used it to implement both actor class sandboxing in the playground by rewriting the code, and also Rust and Motoko canister profiling by instrumenting code. So the screenshot here is actually a flame graph obtained with the profiler in the playground. Finally, we've made it easier for users to embed and share live Motoko code snippets, both in blog posts and in other web content, such as Medium articles. So hopefully this will make it easier for the community to develop documentation themselves. Finally, just hot out of the press, we've got a Motoko code formatter, which people have been asking for. And we've issued a developer experience survey, which we're hoping to get some feedback from users where they want us to go next. So now I'm going to hand over to Kento Sugama, who's going to give a demo of the playground.
All right, thanks, Claudio. Yeah, so I'm going to now demo an update to the Motoko playground. Specifically, this update allowed us to enable actor classes on the Motoko playground. And if you guys don't know, actor classes are similar to object-oriented classes as a language feature, except they allow you to dynamically spawn canisters as opposed to objects. You can imagine this is really useful if you have some sharded system that needs to scale horizontally as demand grows. Yeah, so can I share my screen, please? Okay, great. I'm going to assume that everyone can see this. Okay, so this is the Motoko Playground UI, and here I have an implementation of a very simple distributed hash map. And there are two canisters types involved here. One is this main map canister that orchestrates everything, but really the key value pairs underneath the hood are held by the bucket canisters here. Just so we're on the same page, this is a distributed hash map, so the bucket canisters are in their own canisters. On the right here, we can see the candid UI that exposes two very simple APIs that we're interested in, a get and a put. So to demonstrate this, I'm going to put a key value pair in this map. Notice that when I do this, only the map canister has been deployed. There's no underlying buckets yet. So when I call this function, to cut through some logic, basically the map canister realizes that there is no underlying bucket canister that has been spawned. And the interesting line is right here. This one line lets you dynamically spawn a new canister to hold this key value pair. And you can see in the UI that the child canister was spawned just now. Okay, so now let's make sure that the pair was actually placed in the map. I'm going to do a get on the key that we just put. Okay, and there we go. That's your dynamically spawned bucket returning the value that you just mapped. So this is already interesting. You can now use actor classes on the Motoko playground, but we're going to demonstrate a new extra bonus feature that Claudio just added to the Motoko language. I'm going to demonstrate not only dynamic canister installation, but dynamic canister upgrades. So let's say you want to add a new method to extend the API of this map. Just for simplicity, I'm going to add a clear method that will hopefully clear all the entries of the map. You can see we're getting an error here because not only does the clear method need to be added to the map, but the underlying bucket also needs to be extended. Okay, so I'm going to use the playground to manually upgrade the main map canister. If you're developing on the under the normal circumstance, you might do this with a manual DFX upgrade. Okay, you can now see that a new clear method has been added to this map. But this is where it gets interesting. So what if we want to upgrade the underlying buckets dynamically? I've prepped a method to do that called upgrade buckets that I'm going to call. You can see the logic here. And again, this is the interesting line here, these two. Basically, what this method just did is it iterated through the underlying buckets of the map, found any old canisters that weren't upgraded, and used new Motoko syntax to upgrade that old bucket dynamically. So the syntax goes system to specify that you're using a system feature, the actor class that you're upgrading, and the old instance that you pass in. Okay, let's make sure that we didn't lose any data through the upgrading. I'm going to do the same get, and hopefully we get back the same response, and there it is. But now I can use the extended API with clear. Okay, so if I do that same get again, now we see that all the entries in the map have been cleared. So this is just a toy example that is on the playground, but you could imagine you might use this for dynamically managing the canisters in your distributed systems. And I will paste this example in the chat if you guys want to check it out, but that's it for me. Thank you.
Thank you, Kento and Claudio. I guess we can't advertise the Motoko Playground enough, and I invite everybody to go and try it out and code live Motoko on the Internet Computer. Also, please fill in the developer experience survey that the link has been shared in the chat. So the next last demo is about a topic that is very dear to my heart, and you might have guessed already by now what it is about. And otherwise, you will learn in a few seconds. So when I learned about Bitcoin, my first reaction was, what a waste of energy. And I guess today I would even have to say, what a colossal, gigantic waste of energy. And so, of course, one of the design criteria of the Internet Computer was to do much better and not to waste energy for like stupid tasks, but rather use all energy for something useful, for useful computation, computing canisters, and all of that. And of course, what we have today is still like a version that can be heavily optimized, as you have seen from the compiler optimization that Adam has talked about. Yeah, let me come to the next demo. And I'm so happy that the community has picked this up, and it's going to show us how energy efficient the Internet Computer is. Please, Hamish and Orlando, the floor is all yours. Thank you.
Awesome. Hi, everyone. Can I please share my screen? Can you guys see the slide?
Yes.
Great. So hi, everyone. Yeah, we're Carbon Crowd here. I'm Orlando, co-founder at Carbon Crowd, and I'm joined today by Hamish, who's also a co-founder here. You might know us better as the Internet Computer Footprint. That's the project that we've been working on with the IC behind the scenes. So central to everything that we do at Carbon Crowd is this idea of zero emission technology. We want to build digital infrastructure that isn't net zero, so it doesn't emit carbon dioxide and then that's offset somewhere else, but rather building truly green systems that don't emit any carbon dioxide in the first place, or at least incredibly minimal amounts of carbon dioxide. So that's what really drew us to the IC in the first place, because we see the potential for the IC to be one of the foremost leaders in this movement towards really green digital infrastructure. And we've been working for the past few months on really doing a deep dive into how the IC works and the potential for it to really lead this industry. And we're really excited to share with you today some of the results we've got from that. And they only came out a couple of weeks ago. We've been working pretty closely with DFINITY to do some pretty detailed measurements. And this is the first time that it's being shared with the public. So yeah, I think we're really excited to share this with you today. So from the beginning, one of the preliminary results of our research, which is really exciting, is that we do think that it's possible to basically to build a zero emission system with the IC. It is technically feasible. And the process towards that, we've kind of broken down into 3 phases. The first is the one that we're sort of wrapping up now, which is the baselining emissions. We need to understand the electricity usage of the IC and then be able to collate that with an associated carbon emission. And we're coming to the end of that, and we'll dive into that later in the presentation. Phase 2 is to release a report of all the work we've been doing. We want to be as transparent as we possibly can with this process, share our methodology, understand the limitations of what we're measuring, and have the community and DFINITY at large really see the work we've been doing. And then phase 3, perhaps most importantly, is to implement the most favored strategy. So part of our report will be a series of proposals that anyone from the public or the public can decide on which ones they would like to move forwards on. And we can really start moving towards a zero emission blockchain, and in the short term, a blockchain that does a lot less damage or emits a lot less carbon dioxide. But before we share those results, I want to just quickly dive into how big this problem is. So these numbers aren't the IC specifically. That would be a huge amount of emissions for a single blockchain. But this is basically the cloud computing industry at large. That number in the middle is really the one that you should give your attention to, 2% of global emissions. That might not sound like a huge amount, but to put that in context, it's about the same size as the commercial aviation industry in the world. So it's a pretty massive issue. And what's more worrying about it is that, I think we're all aware of the rapidly digitizing world around us, even before COVID. And what's more, you have other technologies, virtual reality, AI, machine learning, things like that, which are incredibly computationally heavy technologies and are really just growing in popularity. So the chances of that number increasing is pretty high. If anyone's read an IPCC report recently, they'll also realize that we just simply don't have time to waste when it comes to reducing our global emissions. And so the time to really start implementing novel technologies to try and solve those problems is really now. So what is our solution? The core of our solution is a basically computational routing solution, where we take the computational traffic of a digital infrastructure and we run it on data centers that are running on renewable energy at that time. So in a more tangible example, imagine I was trying to load a Netflix video on my phone, and I was in the United Kingdom and it was overcast. The UK's national grid might be running on natural gas. We'll actually send the computation to France, which is running on nuclear energy at that time. And therefore, for the same amount of computation, you would actually produce less carbon emissions. There's other applications you could do, which will be detailed in our report. Things like, running batch jobs at times when the network has a lower carbon intensity. But as I mentioned, that'll all come out in the report, and this is the core to sort of the strategy that we're pursuing. So yeah, sort of made up of 3 parts. Forecasting, we need to understand which data centers are running on what energy mix, and we'll be able to do that to about a 30-minute period. We then route that computation. And then obviously this is a journey. We're not going to get to zero emissions overnight. So we do have the option to mitigate your carbon footprint by offsetting. But as with any real true, strategy for sustainability, the end goal must be zero emissions. So that's a little framing of the discussion that or the research we've been doing. And I want to dive in now. We'll hand over to Hamish to really dive into the results.
Perfect, thanks. So yeah, so in terms of the methodology, we started with gathering all the data of where all these nodes are running for the IC. So what regions they're in, how many nodes are running in each region, the hardware specifications of these nodes, and with the help of DFINITY, also how much electricity are these nodes consuming. So this was actually done by physically instrumenting one of DFINITY's nodes running in one of their local data centers. And then from that, we extrapolated out the sort of estimated power draw for every node. And the reason we felt this was an appropriate way to do it is because DFINITY has specified hardware requirements for each of their nodes. So we know that each node will sort of have similar power draw for compute. We do want to improve this and refine this, and I'll sort of dive into that a little bit more later, as well as in the report. So once we have the rough sort of power draw per region for the IC, we also looked into the emission factors per each region. And this does actually change per region and also per time of day. As we don't have sort of high fidelity information at the moment on the node power draw throughout the day and throughout the week, we just opted for average emissions per region. So as an example, Germany tends to run more on natural gas, so their emissions are actually higher than, for example, France, which uses more nuclear. So that means for every kilowatt that is consumed, so in Germany, more carbon dioxide or CO2 equivalent is emitted. So from that, we aggregate the total emissions for every region and then sort of accumulate that for the total emissions of the IC as a whole. We also sort of pull together the network emissions, the hardware lifecycle emissions, and sort of end user emissions. Currently, these are more estimates based on industry standards and industry methodologies, but it's something that we want to look into more and try and find harder numbers on. So the projected CO2 for the year, as of the current measurements we have, so it's quite a big range at the moment, and we are wanting to gather more, sort of a wider range of data for operating loads for these nodes, hence the large range at the moment. So on the left, minimum, average, and maximum, these are sort of the tons of CO2 that the IC as a whole would emit if running at minimum load, an average load, and if it was running at maximum load for the entire year. Obviously, this will need to be refined more as we gather more information and can refine the model. On the next slide, we sort of dive into a bit more about the refinements. So as I've iterated a few times, we want to get more information about the nodes, sort of how much they're drawing on a sort of day-by-day basis over a longer period of time. We also want to distinguish between boundary nodes and compute nodes because they have different operating profiles. So different loads over different times. And we want to sort of integrate this into our model. We also want to measure nodes in different subnets because different subnets have different distributions of canisters, and different canisters have different call profiles. So it would be more accurate and more representative to measure a node in every single subnet in order to get a more accurate overview of the IC as a whole. But for us, we felt that the biggest sort of improvement to the granularity of our model is in data center specific information. So this is gathering things like PPAs, which is power purchase agreements, which is what data centers do when because they know and they have fairly consistent power usage over the years. So they go out and they buy power directly from solar farms, wind farms, or drawing energy directly from the national grid. And with this information, you can actually get a lot more granular information about how much a particular data center is emitting over a certain period of time. PUEs, this is power use of effectiveness. So this is information such as how much cooling is required, how much energy is being used to cool the data center over and above powering the nodes themselves, as well as third-party and ancillary systems in the data center. Basically, how much compute are you getting per watt going into the data center or per kilowatt? And then as well as water usage and general wastage around the data center itself. This is a growing concern and a growing issue, is the amount of water that is being used to cool these data centers and damaging the surrounding ecosystems. So finally, we're really wanting to put this methodology into the DFINITY dashboard, both for historical and real-time measurements, so that we as a community can see the carbon emissions that the IC is producing, and have an accountability and transparency around the work that we need to do as a community to reduce it and move towards that zero carbon goal. Finally, I just wanted to say a huge thanks for DFINITY, both for this presentation opportunity and as a whole, they've been very forthcoming with information and very helpful helping us out. Specifically to Aisling, who's been our main contact and has been invaluable. And thanks to the community as well.
Thanks a ton, Hamish and Orlando. Very glad to see this and looking forward to see even more from you. So I guess that's the end of our show. And I'm sorry we have a bit overtime, but I guess maybe it's the same for you. To me, this time flew just by so quickly. I could even see more demos probably all day. But thanks for joining. Thanks to all the presenters. And if you want to see more demos, tune in again in 4 weeks on September 28th. So see you then and goodbye.